This is a video on Edexcel GCSE Chemistry Topic 3 on covalent compounds and separation techniques. Let's get stuck straight into this. It starts on covalent bonding. You've got a few of these covalent compounds that you need to know exactly how they're bonding, and then we'll get stuck into different ways of separating some of these mixtures. So let's get the highlights on. Let's go. So, covalent bonding. We talked about ionic bonding in topic 2, where there's a transfer of electrons. Covalent bonding is a bond between two atoms, and they share one or more pair of electrons. So covalent bonds, it can be more than two atoms also. And so covalent bonds lead to the formation of molecules. They can be represented by a simple dot across one, so you can see exactly where each one came from. Ionic bonding as well. So there's 6 simple molecular covalent substances that you need to be able to show using a dot cross diagram. So here's the first one. The first one is hydrogen SH2. So hydrogen needs 2 in its outer shell to have a full outer shell. It starts with 1 because hydrogen has 1 proton, therefore will have 1 electron. So it needs to share that one with another one so that both of these end up with 2. That's what's happening there. Hydrogen chloride, that's HCl. Yet again, hydrogen only has 1 in its outer shell. Chlorine has 7, so it wants 1. Hydrogen wants to borrow 1 of the chlorine, so they share, just like over here. Note that the cross and the dot are in between the circles, and they gap between the circles rather than sitting on each of the lines. You can draw them on the lines, but this is a better way of doing it. Methane, CH4. Carbon has 4 in its outer shell, therefore needs 4 hydrogens to share with it. Okay. There's that sharing taking place. Oxygen, that's right. That's O2. Well, it needs 2 in its outer shell. So therefore, it's going to have to make this double bond, which happens over here. So you end up with this double bond like so. Okay. Water, H2O. That's got 2 single bonds. So you can see those over here and over here and over here. So remember, water, hydrogen has 1 in its outer shell, so it needs 1 more to get 2 in its outer shell. Oxygen has 6, so it needs 2 more to get its 8 in the outer shell. Carbon dioxide needs double bond because carbon has got 4 in its outer shell. It wants 4 more. Oxygen has 6 in its outer shell. It wants 2 more. Therefore, that sharing takes place. 2 double bonds to make sure that all of them have their full outer shells of 2 and 8. So there's 2 main types of covalent substances. There's simple covalent substances and there's giant molecular. So simple molecular and giant molecular. So there's properties of each of these that you need to know. Simple molecular covalent compounds have low melting points and boiling points. So low melting, low boiling points because they have weak forces between the molecules. So they're bound together with strong forces, but the forces between the molecules are the intermolecular forces are weak. So to think about carbon dioxide, that carbon is bonded to that oxygen very strongly, but between that carbon dioxide and another carbon dioxide molecule, there are weak forces, so they're easy to separate. Low boiling point, low melting point. They're also poor conductors of electricity because they have no ions, and they are normally liquids or gases, and they're easily melted, or they can be easily melted to be turned into liquids from being a solid. Giant covalent structures contain a lot of non-metal atoms joined together to adjacent atoms by covalent bonds. So you can see over here they're joined together to adjacent atoms, so in other words ones that are mixed over by covalent bonds. The atoms are usually arranged in giant regular lattices. You can see that structure repeats itself, and over here as well. That's what we mean by lattice, a regular structure, and it's giant, it's repeating itself in a very large way. Extremely strong structures because of the many bonds involved. The diagrams show diamond, which is on the right. This over here is diamond, and graphite. That's this one here on the left. Okay, both of these are giant covalent structures made of carbon. Okay, so substances with giant covalent structures have very high melting points because a lot of strong covalent bonds must be broken. So graphite has a melting point of 3,600 degrees. Diamond does not conduct electricity. Graphite contains free electrons, so it does conduct electricity. So in these layers, there's free electrons that are allowed to conduct electricity. Graphite is made of carbon atoms in layers. These layers can slide over each other, So that means that graphite is very soft, so therefore it's used in pencils, but also as a lubricant. Every time you write, one of these layers essentially is coming off, or some of these layers are coming off. That's essentially what graphite is. Because it's bonded to less electrons than this than diamond, you have a free electron, and that free electron allows graphite to conduct electricity. So diamond is a form of pure carbon, and each carbon atom is joined to four. Each carbon atom is joined to four other carbon atoms, forming a giant covalent structure. As a result, diamond is very hard. It also has a high melting point, and it doesn't conduct electricity as well. So it doesn't have any free electrons, so it cannot conduct electricity. Graphite can only conduct electricity because of its free electrons. It has layers, and therefore it's a good lubricant and can be also used in pencils. Diamond is joined to four other carbons, therefore it's very hard, has a high melting point, and does not conduct electricity. So you need to know how to classify elements. Okay, essentially use these ideas of properties of structure, like whether it can be dissolved, talking about solubility, knowing the melting point and boiling point, to decide whether and whether they conduct electricity, to decide whether they're covalent simple molecular, covalent giant molecular, or ionic. So sodium chloride, magnesium sulfate, and copper sulfate all conduct electricity when dissolved, but not when they are solid, so they are ionic. Hexane and liquid paraffin do not conduct electricity, so they can't be ionic. They have low melting points and boiling points, so they've got to be simple covalent. Sucrose doesn't conduct electricity, so it can't be an ionic compound. It has a low melting point and is soluble in water, so it must be simple molecular. Silicon oxide doesn't conduct electricity, has a high melting point and boiling point, so a giant covalent structure. So that's how we classify. Think about the boiling point, think about the melting point, think about whether it conducts electricity, think about whether it conducts electricity when it's dissolved. So we've got a few separation techniques. There's a separating funnel, which is very, very straightforward. There's fractional distillation, which we know a bit about from crude oil. And then after that, there's chromatography. So let's go through the separation funnel first. Miscible liquids are ones that mix together, so they'll do is like milk and tea. Immiscible liquids are those that don't mix properly, so that's like oil and water. Immiscible liquids can be separated using separating funnel. The two immiscible liquids are shaken together and are allowed to stand until they separate, like the oil and water has here. The less dense liquids on top, the more dense liquids on the bottom. The tap at the bottom is then turned, and the more dense liquid is drained away into a beaker. You then tip the liquid that's on the top out, or you could drain that again. But the better option is to tip the oil out from the top. Fractional distillation. Miscible liquids, so such as like liquid air, can be separated using fractional distillation. Nitrogen and oxygen are obtained from liquid air in this way. So air is filtered to remove dust and any other particles that are in there, and it's cooled to minus 2000 degrees Celsius. At this temperature it's a liquid, so we can say the air has been liquefied. So this is what happens as the air liquefies. The water vapor condenses, is removed by absorbent filters. Carbon dioxide freezes at minus 79. That's then gone. So you're left with oxygen, which liquefies at minus 183, and nitrogen, which liquefies at 196. So liquid nitrogen and oxygen is separated by the fractional distillation. The liquefied air is passed into the bottom of the column. So you pass the air into the column. So just like it's used with oil fractions, this is then warmer at the top than so it's warmer at the bottom than at the top. So it starts to warm it up. Okay, and therefore certain fractions come off there, certain parts. Liquid nitrogen falls at the bottom of the column. Gaseous nitrogen rises to the top. It's piped off and stored liquid. Oxygen collects at the bottom of the column. The boiling point of argon, the noble gas that is about 0.9% of air, is close to the boiling point of oxygen. So a second fractionating column is often used to separate argon from oxygen. So essentially, fractional distillation uses differing boiling points to allow us to separate out different gases. Chromatography. So chromatography can be used to separate and identify components of mixtures. So say you've got a coloured pen and you want to know what colours are within it, you could use the chromatography to do it. Also it can be used for colouring agents and foodstuffs. So if we look at these dyes over here, here's our solvent. Okay, here's our solvent front, so it's been allowed to sort of rise through here. Here's one of our dyes, one of our ink spots, sorry, and here's another one of our ink spots. You can see that the ink spot on the left is made up of this colour here and this colour here. You can see the ink spot on the right is made up of this colour here and this colour here. So you can see they have one dye in common, but they have two other dyes which are not in common. Not in common, sorry. The RF value of the chemical form, of chromatography allows you to identify chemicals within the substance. So essentially, what RF value is allowed to do is to identify chemicals within the original substance. The RF value is calculated using the following formula: as distance travelled by the substance divided by distance travelled by the solvent. So that would be the distance by the substance, and that would be the distance by the solvent. And you divide one by the other, that gives you the RF value. So scientists keep an eye on table these RF values so they can identify substances such as food additives or drugs. And that is the end of the topic 3 video on covalent bonding and classifying materials and separation techniques.